All right, Brevin. Today, Brevin will be talking about coarse geometry and how it relates to asymptotic dimension. Okay, Brevin, you should be able to share your screen and I'll mute myself.
Yeah, let me just get this pulled up. Give me just a second. I'm seeing if I can pull it up somewhere where I can draw while saying my notes at the same time, which would be really handy here. I should have grabbed this while we were talking. Can I drag the PDF into OneNote? Will that work? I have a feeling it won't, but I had to try.
You can,
Oh, it did.
you
It did.
can,
Okay, I got
yeah,
it.
yep.
Okay, cool. I figured it out. It took a second, but I have it. All right, now can I just share my screen on OneNote? Da, 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 da. Sorry, little new to this whole thing. It's been a while since I used Zoom. Share screen and course embeddings in OneNote. Okay, are you able to see my notes here? Is
Yep.
that a yay? Okay, okay. And I can draw, right? Cool. All right. So yeah, the next topic here is course equivalence. This is something course geometry I care quite about because it is really important when one wants to understand hyperbolic geometry. That's where this first comes from. And then, of course, it was extended to these far more vast settings, which we'll talk about here. So everything here will be in the context of general metric spaces that we're going to present, because that is what is important for the asymptotic dimension and for some of the later results. But of course, I'm going to mention some classical results here at the end where classically these metric spaces are going to be hyperbolic and manifolds, is where a lot of these notions first arose. Um, so isometries are very classical. So the notion of an isometry, in case anyone here isn't very familiar, is something that should preserve all of the geometric structure of a between two spaces. So isometries preserve distance. Turns out that's basically sufficient to get everything we need. If you can preserve distance between two things, you can preserve everything else. Generally, that is a very strong condition for some type of lifts. So the goal with all of course geometry is, can we lift things to where they're close? So kind of pictorially, you might have what's the best way to visualize this? So I think best way to do it is Z and R, because we've talked about that a lot. So if we have the real line here, and then we have our integer points here. Our integer points there's not a nice map that goes directly from Z to R and is going to be an isometry. The distance here is a little off between things, because in R, for example, there can be distance one half, and that's not going to happen in Z. However, it's still coarsely equivalent, and I'll define that here. But the idea is that these things should be close enough that within some balls, up to some fudge factor, some additional constant fudge factor, they should be the same. So the general definition of a coarse equivalence, or first a coarse embedding, is that instead of just having that the distance between points is same as the distance between their images, which would then be, again, the same as the distance between the points, we instead bound them between two functions. So we have functions going to infinity. In your head, think of the identity functions here as a first example, because that's what gives isometries. Um, they will, in general, not be the identity functions, but we often choose them to be actually particularly close. The most common ones here are going to be quasi-isometries. So the notion of a quasi-isometry is you basically choose the row one and row two to be linear, is your goal. So, due to some shenanigans about rescaling to choose worse constants as necessary, we can always assume that it is of the form given in this result, whenever row one and row two are linear, where it is 1 over a times the distance minus b below, and A times distance plus B above. That is kind of the most common case of a coarse embedding, you'll see. And because everywhere within geometric group theory and geometric topology are going to be using quasi-isometries to preserve something. Quasi-isometry is the key word for I'm preserving something in geometric group theory. Um, Coarse embeddability in general, as we're going to do here, does preserve asymptotic dimension. So asymptotic dimension will be preserved under a slightly more broad category. This is the right category for that notion of dimension. But I would keep quasi-isometries as the example in your head because it has a lot of canonical examples you can pull from to imagine that. The general case can give much more vast functions. You could have functions that grow exponentially as opposed to linearly, and that can cause your notion of closeness to differ, but should fundamentally still be the same idea. Um, one important thing to note is that these things are in fact injective. That's You would want that for the notion of embeddability. You want it to be a homeomorphism onto its image. That is not going to happen in general. Unfortunately, these things aren't always continuous. There is a restricted notion that is continuous, I'll talk about later, called pseudo-isometries, that are very useful. Quasi-isometries in general, and then definitely coarse equivalents are not going to be continuous though. The but injectivity just comes from a injectivity is immediate due to the fact they're non-decreasing. And the other important thing we're going to need here for later is that they are distance non-decreasing. That the map F is, so these coarse embeddings. So clearing up the terminology here a little bit, there is going to be a few different things here. Whenever I say the word embedding, that is going to be the map without a surjectivity condition. When there is a surjectivity condition, we use a slightly different phrase. So we have coarse embedding and then coarse equivalence. We have a quasi-isometric embedding and a quasi-isometry. We have a pseudo-isometric embedding and a pseudo-isometry.
Can I ask a question, Previn?
Yes.
So rho one non-decreasing, the condition that rho one is non-decreasing, does it mean that in some way we are not collapsing the distances as well to preserve some sort of structure? This rho one, like if we had just one side, even in quasi-isometry, if we had just one side of inequality, that is the right-hand side,
Yeah.
then we know that the distance of image is bounded linearly by the distance of the domain,
Yes.
distances in the domain. But the lower bound, the first inequality, does
Mhm.
it in any way bound or tell us that we are not collapsing the distances because of which we are preserving some
Yeah.
sort
Yeah.
of properties?
Yeah. I mean, I think it's easier. So there's two things that are distance non-decreasing. The thing that I underline in green is F, of course, which
Mhm.
is the map itself. But regarding row, that was a bad underline. Regarding row one and row two, which are non-decreasing here, you are correct that with quasi-isometry, what we want to do is zooming out. We can shift our balls around by B, and then we can rescale by A. So we're looking within certain balls, and within those, we're saying it's vaguely an isometry within this ball. The notion of a coarse embedding in general is a little bit more complicated, but you could certainly try to do like the same notion. It's up to examples of this tend to be like I haven't encountered. I looked up some papers on coarse geometry and I looked through some examples. They tend to be rather, for me as a concrete low dimensional geometer, they felt rather arcane. But certainly, when row one and row two can be chosen to have some structure, which appears to be often the case in practice, I'd say the answer is yes. As a general paradigm, like within the most abstract contexts, I don't know if there's like a natural domain you could choose for row one and row two in which you could look at the geometry and have it be the same. It's certainly supposed to be analogous to what you said, but I don't know if there's like this notion of a ball or something we could look in and say like it looks like an isometry here because they can grow just so far apart. And if it's growing exponentially, then you're not going to be able to restrict it by nice balls. Maybe you could look at like domains that grow exponentially and look within those, but I haven't seen anyone attempt that.
I see. And one more question. So you mentioned that coarse embedding, it need not be a homeomorphism in general, but
Correct.
quasi similarly for quasi isometry, it need not be a homeomorphism in general because of Z, and our example is an example where it's
Yes,
not an homeomorph, right?
correct.
Okay.
Yeah,
Okay. Awesome. Thank you.
yeah. Continuity is going to be an important thing. Um, to get later on here, we're going to define a notion of a pseudo-isometry, which is the exact same thing as a quasi-isometry, except you just cross out this plus b on the right side. And importantly, that means that it is if the distance between f of x and f of x prime is less than the distance between x and x prime up to a factor of a, that's the same as being a Lipschitz. Obviously, Lipschitz things are continuous. So this fudge factor of b on the right is really the only thing that prevents continuity in quasi-isometry. And if we can get rid of that, which is important for some results, we can get continuity. So they're very close to being continuous. They're only potential, like you think of them as being continuous up to the fact stuff could be shifted around by B all over the place in our area. But at a global scale, these things are continuous. Like if your notion of continuous is things that are close before stay close together in the end, then yes, these are close. They're just close after we group stuff by balls of size B, basically. But within those balls, stuff can get perturbed in a little bit more ugly way, is how I think about it. Any other questions? Did Manisha just is she gone? Oh, welcome back. Welcome back. Okay, so as I mentioned before, we can upgrade this to coarse equivalence with a surjectivity condition. So the precise surjectivity condition we need here is that we have our space X, we have our space Y, and it might happen, let me draw this a bit bigger. It might happen that our image of X will end up within our space looking like we imagine it kind of as a bunch of dots spread throughout our space Y. Um, I don't know if I should talk much while she left because I don't know if it's recording on her end.
Manisha, you're muted.
Yeah.
Oh, I just said I'm still here. I just muted myself. I just turned off my video because I was walking to get a
Okay.
better internet connection.
Oh, sweet. So it's still recording. Okay. Okay. Then I'll keep talking. Just was just making sure. Um, okay. Then we imagine we take our space X and we embed it in our space Y, and we imagine in general a lot of little dots. Around each of those, we hopefully can find some distance C, such that if we surround all of these things by C balls, ideally that would cover our whole space. So the radius here is equal to C. Any questions on it? So it's surjectivity almost. Again, we think of these things as globally being basically surjective, but issues around here. If you zoom in and view the fine details, it might not be surjective precisely, but it's almost surjective in that there's always something close enough. Um, one of the key ideas here, and we'll go through the proof of this. So a lot of this is filling in exercises that were left in the note. Well, they were claims that were made in the paper that were made without proof. So I'll fill in some of the details of this I went through. So one of the key ideas is this equivalence right here. So a priori, we don't know coarse equivalence, which is, as a reminder, when we have a coarse embedding with this surjectivity condition, we don't know that it is an equivalence relation. So that is one of the basic things to prove here is that this is an equivalence relation. You would expect it to be. It's called a coarse equivalence, so it better be. But a priori, this definition is not symmetric because y being a subset of a neighborhood of f of x does not necessarily mean you can go the other way and get x as a subset of some image of some coarse embedding of y within a region C. So that is precisely what we do here. The entire purpose of this lemma basically is to show you can go the other direction. So if you know x is coarsely equivalent to y, so there's some coarse embedding f going from x to y, satisfying this surjectivity condition, then that means we can basically just go immediately the other way. There will be some g. So the one direction, as I mentioned, is just immediate. If you have the second condition, if you choose some point in your space y, then we know that the point y is within, because it's C close to the identity, the compositions here. We know that y and fg of y are both, the distance between them is less than C. And that just gives us a result immediately. And vice versa. So the second condition is a priori much stronger than the first one. And the goal is to prove they are equivalent here. Any questions on that? Okay. So first we have our space X, we have our space Y. X has a line there. I know my alphabet. Okay, and here's F. Um, so a priori we have some coarse equivalence here. To define the point, the map G, you can actually be rather loose with it. The idea is inside of this space Y over here, we have our image of X, we have all these points that are spread out throughout it. And if we choose some point that is not red, say this green point right here, we look at some neighborhood around it, and there should be some red dot within that. There could be a lot of red dots within it, in fact. We then grab some red dot and we pull it back to any preimage of that red dot. So there are a couple choices here. You get your choice of red dot in each region, and you get your choice of preimage. A priori, that might sound like there's choices to make, but when defining G, we just fix that. Like we define a fixed G by just going region by region, and we just choose one inverse for each of them, which it becomes a well-defined map G once we do that, because you just choose the thing that's within your local ball, and we've chosen a preimage for every point. We've chosen it to be one of them. It obviously won't be continuous or nice in general because we had so much freedom in how we chose this thing to work that we might have chosen really bad preimages that weren't continuous. But it will be a well-defined map in that we know where everything goes to. Um, yes. Any questions on that? Okay. So we know we can choose a point. Um, so given a point y, this green point. So this green point here is the point y in our proof. And some pre-image of it is x. So we know that there's some little x over here that gets mapped to this red point, some red point within this region. And we define the pre-image of y to be x under this map G. So G takes y to x. Importantly, we now know that because it's non-distance increasing, you can show that the distance between x and g of f of x is less than c. Yeah, so given x, we then know g of f of x equals x prime for some x prime. So this point in just detailing this so you guys can follow along with my notes later, this point here would be x prime. Yes.
Can I ask a question?
Yep.
Why does it matter? So here, since you have a red point, you take its basically its pre-image is x.
Mhm.
F of x will go to that red point, right?
Yes.
Where did we use the fact f is distance non-decreasing?
Yeah. So let me just go line by line here to be a little clear as opposed to skipping around the proof. So now I've explained the idea. So we take our map G, we define it by taking our point y here, this green point, and we find our point x and f of x such that the distance between them is less than c. So I guess let me let me be a little precise on the notation I'm using here because I'm abusing notation on what is X and what is not X. I think I chose this to be I think I chose the point itself to be X right there. Um,
Mhm.
I think that might just be a typo. I think I should have. Oh yeah. Oh nope, that was just a typo. Okay, yeah, this is X. This is the point f of X. That's a typo in my notes. Sorry. Um, so we can choose. Then we let g of y be X. So you're okay up to that point.
Yep, yep.
So we have our point X. G of y goes back to here. Um, so given this point X over here, we know g of f of X, which so wherever g takes this point here
Mhm.
is going to be X prime with some for some other X prime. So the idea is we chose we know how to take every point in Y back to a point in X. That's what G does. It has to do that. So it takes this green point back to this orange point. Sorry, this red point. It takes the green point back to the red point. This red point was the over on in Y was the image of the red point in X. The problem is the image in Y might actually pull back to a different red point X prime, is what happens.
Mhm. Ah, okay.
So they're all separated by distance c, but because we have all this choice involved, we might take a point x, map it forward. We have our point y. It's close to this point that was mapped forward, so we pull it back to its pre-image for the point y under g. But G might also pull that point back somewhere else. So G can complicate stuff. So this is where I said it's not really continuous in a sense because X prime and X need not be anywhere near each other. So we took our point X, mapped it into our ball. Y was really close to it over here, so we could pull Y back to it. But this point f of X might pull back under G to something wildly far away, a priori. So
Mhm.
our goal is to show that that doesn't happen. So that's where the distance non-decreasing comes into play, is so we can bound this stuff between X and X prime. We want to show that they aren't too far apart. So given this point X, we know that G pulls back f of X to some X prime, and the distance between f of X and f of X prime must be less than C. Because again, we now look at the distance where X prime goes to, and that's some other point here. So there's now f of X and f of X prime, both living over in Y. I know there's a lot of arrows going back and forth. There's a lot of labeling as we push stuff forward, pull it back, push stuff forward, pull it back. Since f is distance non-decreasing, though, this condition here, we can just drop the f's. That's the important part. You drop the f's on that, and that gives us that the distance between x and x prime is less than c.
Okay, got it. Mhm.
So essentially, we're using distance non-decreasing to use the fact that we can get stuff bounded within a c-ball. X prime was defined to be g of f of x. So that is what tells us that the distance between x and g of f of x is less than c. We can then do the same proof backwards, essentially, with y. So the core concept here, as stuff is pushed around, is we can define a lot of images and pre-images of points, but we have to be really careful because in general, when one is doing math, you define an image and then you define its pre-image, and those nicely correspond to one another. But in this case, when you're like trying to prove injectivity or something, it gets more complicated than usual because you have your 2 points, they're images, and then different pre-images they pulled back to, and then different images they push back to. But everything on in Y should be within a C-ball, everything within X should be within a C-ball. So you just use all those bounds and then show that it all works out, essentially using this distance non-decreasing.
So why you have your f is distance non-decreasing?
Yes, that comes just from the definition here. Because
Oh,
the
okay, okay.
distance between x and x
Mm,
prime is less than, oops, undoing, I forgot undoing, scrolls this down, is less than rho one of the distance, which is less than
mm.
the distance between the images.
Yeah, because your row one is actually non-decreasing, right?
Precisely, yes.
Yeah,
So we
yeah, okay.
we get the distance non-decreasing from f for free from rho one.
Mhm. Yeah, thanks.
There's also a condition we'll need here later. I don't think I mentioned earlier, but we do need, it's a minor technical condition. We do need that the rho one the limit of points goes to infinity. We basically just need it to grow. It's it would be weird to come up with an example that didn't grow because suddenly your distances are collapsing on each other. That would be a very, very weird bound indeed, especially since we're bounded on both sides this way. They could potentially flip and it would cause all sorts of problems. So we just want both of these things to grow. Again, think of the identity function. The function x grows. It should vaguely look like the function y equals x. Okay. So the importance in this whole proof here is that this second condition is symmetric. So you go through some shenanigans here to prove injectivity. Again, if there were some details in the proof I skimmed over a little too fast, don't worry about the details. You can read them. You can think about it later if you want to, but the important part is there are some shenanigans about pulling stuff back. All of this we do just to get this symmetric statement between things so that we can prove there exists a coarse inverse. And once we have the coarse inverse, everything in this starred statement here is entirely symmetric in x and y. If you have a statement that's entirely symmetric in x and y, that means we have a what's it called? Reflectivity? What is the statement in a equivalence relation? I think it's called reflexive, is what it's usually called. So this shows the reflexive property. We of course have the fact that x is coarsely equivalent to itself. Choose the identity map. So all that remains to prove it's an equivalence relation is transitivity. Transitivity is, this one took me a little bit. It's a short proof, but figuring it out was a little bit weird. So let me just go line by line through this one to explain this. So we have some x here, some y here, and some z here. And we have our f here and our g here going between these spaces. And these are each f and g are coarse equivalences with constants. So there's a constant C1 here and a C2 here. These constants C1, C2 are corresponding to the C's here. So they are the neighborhoods we need to choose to get surjectivity. Okay, so we choose some point Z in little z within our space Z. We know there must exist some point Y, some little y over here, such that its image is close to Z when you map it under G. That's what it means to be a coarse equivalence. And it'll be bounded by this constant C2. Likewise, given Y, we can pull that back to a point X here, such that distance between f of X and Y is going to be bounded by C1. We then actually need to specifically use the definition of row 2 here in the that comes from G. So as a coarse embedding, G gets an upper bound row 2. And we have that the distance between G of Y and G of f of X is going to be less than or equal to row 2 of Y of f of X. That just comes from the definition of a coarse embedding, in that row 2 is the bound above. And if you want to bound a distance between images, you can drop the images, but you have to add that row 2 bounding from above. So we had Y, f of X on the inside. We had the images of G outside. We can drop the images of G. We just have to bound it now by the row 2 coming from G. And that is the distance between Y and f of X is, of course, C1 here. So we get that's bounded by row 2 of C1. Because row 2 is distance non-decreasing, so it preserves the inequality. Questions on that so far? Okay.
Like also we can use the inverse function, right? The thing that we just proved, like because f is a coarse equivalent, so there exists a y to x, and also there exists for z to y. So
Yeah.
compose that also. That will be the inverse of f compose g, like the coarse inverse.
Yeah. 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 You can certainly do it that way. Yes. Yeah. Yeah. You're right. That's actually maybe simpler here.
Because there is no bound on the constant, right? If I
Yeah.
get any constant, like if my inverse is the distance between the inverse and the original is some constant bounded, but then I'm done, right?
Hmm. Yeah, that's a
So
fair point. Yeah,
yeah.
yeah, that is clever. In any case, we're done. Either via that argument, via the triangle inequality, we're done. So essentially, we just have to be a little bit careful in the details here, but we get transitivity. Now, now that we know it's an equivalence relation, so we can group stuff up to this notion of coarse equivalence, we want to see how this plays with asymptotic dimension. So what we do is we consider a cover of our, how do I say this? Yeah, first there's an observation to make, which is that if we have y as a subset of x, then if we've covered x with an R multiplicity cover, we can just restrict that to y. That's great. So we have a cover for y, which means that if you have a subspace, that might be the correct cover for y. That gives the asymptotic dimension. But there could also be a smaller cover. As a good example to have in your heads, we could just take R2 and look at R within that. And if you cover R2 in any natural way, like via some type of tiling, you look at what this looks like on the real line, and you'll get you may get a bunch of intervals, you may get something weirder. It depends on what you've chosen. So it may happen to be that on a subspace, you've chosen something that has the minimal amount of intersections of stuff, or it could be it's only minimal in the bigger space, but you can actually get a little bit smaller by choosing a more clever partition in the subspace. So this tells us that asymptotic dimension preserves inequality of subspaces in the sense of ordering. So if y is a subset of x, that means the asymptotic dimension of y is less than or equals the asymptotic dimension of x. The notion of coarse equivalence tells us the opposite is basically true. So as long as we've embedded the subspace in a way that it's close enough to filling up the ambient space, we're done. It can't only take up a small amount. Like R here is bad. R only takes up a very small amount of R2 is the problem. It takes up a single line. But if we were to choose, for example, Z2, Z squared, Z squared fills up our space in the sense that we can actually find little balls around everything to cover R2. So we want that coarse equivalent spaces have the same asymptotic dimension. So we have X and Y as our metric spaces as always, and F is our coarse equivalence between them. We're supposed that asymptotic dimension of X is less than or equal to N. So there are going to exist R disjoint families, U0 through U1, of uniformly bounded subsets of X whose union covers X. That was one of the conditions we had last time, one of the four equivalent conditions we had for asymptotic dimension. Again, in your head, you should think about this as just as a reminder, like here might be red might be U0, green might be uh I've chosen a bad let me just color in the picture up here. You would have that like U0 and U1 would be like you would want to alternate in colors or something between this so things wouldn't touch each other. Something like this. You can find these families that are disjoint from each other, but are also uniformly bounded that stay apart but cover the whole space. So the idea of this, the whole idea here is that we look at any one of our families, so any one of these colors, say the blue sets or the green sets or whatever, we look at any two elements of those, and we have this inequality. We know that they are R disjoint, so that means the distance between U and U prime is bigger than R. Row 1 is distance non-decreasing, so it takes that strict inequality, turns into a weak inequality. Up above, basically the exact same thing happens. We know the distance between these things is bounded by D. So turns it into a weak inequality up above. In between these, by the definition of row one, row two, the distance between the image will be bounded between. So in terms of the families, this says if we are looking at the families f of ui, each of these things are each also row one of R disjoint and row two of D bounded. So we get disjointness and boundedness for free coming from if we map these images, these families UI under F. Time we have 43. Okay. Um, the formality of this requires there's a little bit more work here because this middle condition, essentially what we need to do is this middle condition here. Technically, this is an incorrect line to just write in the way I just said it because this is working on the level of sets. Whereas we proved the definition of coarse embeddability is a priori only for elements of the things, and the distance between sets actually has an infimum in it. So there's an infimum in here. And if you just tried to naively follow this argument here, you would end up with a like an infimum inside of row one and an infimum inside of row two. And you would have to then argue you could interchange the infimums inside and outside of row one and row two. Instead of doing that, it's easier to just get around that problem by doing the classic real analysis trick of choose anything. If you want to take an infimum of things, take something, prove the bound, and then take an infimum of both sides. Basically, just take a limit of the things as they get smaller, gets rid of this whole issue. So what's formally happening is we actually have row one of R is less than, so this thing here is still perfectly well defined because that was just our assumption, basically. That's row one preserving inequalities and is our assumption. This thing here, the second step is what we actually need to be a little bit more formal. The distance between the points is less than or equal to the distance between the sets, sorry, is less than or equal to the distance between any 2 points in the sets because there's an infimum inside of there, which is less than or equal to the images. You then just tack on infimums and you're done. And then you do the same thing on the right side. So this is just formal shenanigans to make everything technically work. But the argument that was given up above, that one line thing, is basically the core of the proof. We now have weak inequalities. If we want to, we can always, of course, upgrade them to strict inequalities if we want. All you have to do is divide by 2 or multiply by 2. Now we're back to strict inequalities for disjointness and boundedness. Any questions? Okay. So we know by coarse equivalence that because we have our map going from X to Y, we know that there will be some neighborhood around f of X that covers Y. Remember, think of X as a bunch of points inside of Y. There will be we can cover it with a bunch of balls around all those points, and those will cover Y. And so the R here, I think we called C before, but following the notation of this paper, they used R. So because of this, just mapping under F, we know that or how it says, so we know Y is partitioned into, we know X is partitioned into all these UIs. So here's our partition of X. We know a neighborhood of f of X covers Y, so a neighborhood of all of the images of these pieces covering X should cover Y. And because of that, that will still be disjoint and bounded. All that could go wrong is these images now. We've covered things in such a way that we've covered them with R balls. So our balls could have gotten things a little bit closer. Our balls all have radius R. So we could have gotten R closer within each of these balls. So we have to subtract 2 from the disjointness, and we have to add 2 to the boundedness because they get 2R bigger, each of these potentially. Because again, we're looking at the points, our points X live within here. And that's originally the things that were disjoint and bounded. But we've kind of pushed them closer by now considering these cells, these families. So they're potentially less far apart and they're bounded by bigger things, but they are still disjoint and bounded. Importantly, row 1 and row 2 get bigger. Because they get bigger, going to infinity, it doesn't matter that we've subtracted a finite constant from them. Just make them really, really big. And now they're as disjoint and as bounded as we want them to be. Oh, well, as disjoint as we want them to be. Preferably keep the bound small. But importantly, you can make row 2 big enough that the 2r doesn't matter. It's just uniformly bounded. Yes. And then, of course, if we can make it r prime disjoint for any large enough r prime, that means it's r disjoint for any r greater than or equal to 0. So it satisfies the precise condition we needed. Since n was arbitrary, this was any cover we chose, we get the result. We get that the asymptotic dimension of y is less than or equal to the asymptotic dimension of x. So it is preserved in one direction under coarse embeddability. Of course, if we have a coarse equivalence, we have a map going the other direction, and we're done. We get inequalities going both ways, and they're equal. Yeah. So any questions on any of this? So this was all the stuff that was in the paper. This all comprised about one paragraph in the paper. So a lot of what I wanted to do here was to fill in the details of these proofs, which I think were all relatively straightforward proofs, but probably needed to be said. At least because I think they explain kind of the ideas of what's going on in these with coarse embeddability. These are the standard arguments one uses to prove these. But yeah, any questions? Okay, then geometry, my favorite part. So pseudo-isometries. I mentioned before, the pseudo-isometries is just a quasi-isometry where you've removed this part. So they are Lipschitz. This definition was originally due to Thurston, and so I think people had considered quasi-isometries certainly before, but they hadn't. This was kind of the first major use of it that made them really, really renowned. And of course, then that was extended to Gromov hyperbolicity, and then all this stuff was expanded to like delta hyperbolic stuff in the group theoretic setting, and then to general metric spaces via like length metrics and so forth afterwards. I wanted to mention why I care about quasi-isometries and pseudo-isometries. The idea is you'll recall that if you have any map F going between spaces X and Y, satisfying a really weak condition on the fundamental groups, we can lift that to a map between the universal covers of the spaces. That the lift will be continuous. That's about all we know. If you have a continuous map down below, you can lift it to a continuous map above. It turns out you can get a lot of strong conditions when you have hyperbolic spaces. So the first result here is if we have a space M and a space N, and we have a smooth homotopy equivalence between these. And we want them to be closed. You can weaken closed to like finite volume if you want, but the proof gets a little more complicated. But if we have closed things, any lifting map we have here is a pseudo-isometry. So somehow, just looking at homotopy of these things, also n is greater than or equal to 3. That is important because Teichmuller space exists. Yeah, you do not get this rigidity in dimension 2. So in dimension 3 or above, we have that any smooth homotopy equivalence between closed hyperbolic N manifolds will induce a pseudo-isometry when we lift it up above. So somehow what happens is this homotopy, which is a priori a very weak condition on how stuff could be bent or moved around, hyperbolic stuff tends, the way I think of it is the curvature. When you have sufficient curvature in enough dimension, it bends stuff towards each other. Because stuff is bent towards each other, we end up with stuff close enough to being an isometry. It'll get bent within some ball, and it could do some wild stuff within that region, but it will stay close enough. It's almost an isometry. When we pass to the universal cover.
Can I ask just one question?
Yeah.
Does this is sort of very rigid statement about the lifts of smooth homotopies?
Yes.
And do you know, like, is there also classification of smooth homotopies on between two closed hyperbolic N manifolds? Like, do we know how F generally looks like F can look like. For instance, F cannot be, let's say, I cannot think about any map. Maybe something like quasi symmetry, or I don't know, like F has to be of this form. Do we have any condition on any classification for F as well?
Yes, that is Moss rigidity, which I'm getting to.
Um,
That's the whole point of Moss rigidity. So Moss rigidity, I'll just say it now, is the idea that in dimension greater than or equal to 3, essentially every aspect of your manifold is determined entirely by the is entirely determined by the fundamental group. So we have pi 1m determines everything. It determines your distances, your lengths, your volumes, everything. You can think of that as a very special case of extending Gauss-Bonnet. Remember in Gauss-Bonnet, we have that the integral of our curvature times the area form is equal to 2 pi times the Euler characteristic. And if we have curvature k equals -1, which would be hyperbolic, then on this left side we get the negative area of our manifold because it's a constant. Pull outside the integral, integrate, you get the whole area of the thing is equal to 2 pi Euler characteristic. Of course, the Euler characteristic is negative, so makes sense. Often you'd move the negative over to the other side, but that tells us our area is given in terms of a topological thing. So the volume of a hyperbolic surface is actually a topological invariant. So what looked geometric was actually topological. This is basically the same thing. Mostar rigidity says even further in higher dimensions. So first of all, you still get that volume as a topological thing, but now everything is topological as well that you could want about the geometry of your surface. And in particular, your question about smooth homotopy equivalence. Well, if you have a homotopy equivalence, that's going to induce a equivalence on pi 1. And if you have an equivalence on pi 1, we're done. Because that will restrict us to essentially the exact same geometry here. And so your map F, like, yes, there's some things it can do, but because there's only one geometry here, you just kind of quotient out by whatever your action is on your action on HN, and F will basically be that. There's some fudge factor that needs to happen here because we've taken a lift. So there's technically a lot of copies in the universal cover you could quotient out to. You might quotient out to the wrong copy of F, like something. It won't actually be F. It will be just something else that lifts, but it'll act like F. So then your notion of what are the maps F you could get your smooth homotopy equivalences? Well, they're basically just going to be they're going to be quotients of automorphisms of pi 1, essentially, is all it's going to be. Um, and then the other piece that goes into Moss rigidity is this. So Moss rigidity, as stated, doesn't require talking about quasi-isometries at all. It just turns out the entire proof of it requires quasi-isometry because you start with a homotopy equivalence, you lift that to a pseudo-isometry. You take that at pseudo-isometry and you lift, which is now on the universal covers. The universal covers are, of course, HN, the hyperbolic end space. You take those hyperbolic end space isometries and you extend them to continuous maps. There should be a boundary here. Sorry, a line there. You extend them to the boundary, and you show the restriction to the boundary as a homomorphism, which gives us all of this restriction. So the goal here is that you can take a smooth homotopy equivalence and lift it to a continuous map on the closure. But in order to do that, you have to pass through a whole lot of stuff about quasi-isometries in between, because you very much use the fact that the reason you use pseudo-isometry here is that the boundary of hyperbolic space is given by equivalence classes of lines. In hyperbolic geometry, if this is like our Poincaré disk model, your points at the boundary here are going to be equivalence classes of geodesics, which come in towards this thing. And that is the definition of a boundary point, is equivalence classes of geodesics. And what you need to know is that these geodesics play nicely, and knowing all of this isometry condition, it essentially allows us to go through the proof and say they play nicely enough that we can conclude that the key point you need to conclude here is, first of all, that's continuous and that it's injective on the boundary. Injectivity follow, and both of those follow pretty much immediately from the isometry condition. It's only about the whole proof is only about 2 to 3 paragraphs of Moss-Style rigidity. It is a very strong theorem with a very short proof. But first you need to prove this statement, which is the longer one. Okay, that concludes all
Also,
my
I have
items.
I have one question.
Yeah.
So it's like, look, you mentioned like that you just need a pi one of your M to fill the gaps in the F tilde map, right?
Yes.
So is this because like pi one of M and the M tilde, like the universal cover or quasi isometry?
M tilde is hyperbolic space.
Yeah. Sorry,
What
pi one
was
of.
what was the end of your question?
So why you do care about like the pi one of M only? Like whenever you're talking about the lift, you told something on the pi one of. So if I have the information about the pi one of M, then
Yeah.
you'll end up with the information of this one. So
Yeah. So the idea is that through this process here,
right.
um, these together reworded in the language of geometry, because these aren't worded these aren't worded in very much the language of hyperbolic geometry. But if you reword them in hyperbolic geometry, what ends up happening is you get,
Mm,
if you have spaces X and a space Y here, um, and these have the same pi 1m,
right.
if they have the same pi 1, that will, because of this pseudo isometry you get here, this will carry all of the things we need on the interior, and on the homomorphism on the boundary will carry everything we need on the boundary. So it will carry over any topological information, but also,
Mm,
so like these things will have the same volume, they'll have the same uh spectrum, they'll have the same like et cetera, et cetera. So the whole point is pi 1 is sufficient to calculate these things, because all we need to look at is homotopies. Any homotopy,
okay.
any homotopy can be upgraded to a smooth homotopy. That's just Whitney's theorem. And then and of course we want an equivalence here between things. So we
Mm,
assume there's a map going backwards, but having the same pi 1 exactly says that we can go
all
forward and
right.
backwards. So
Right.
we this is not worded in the language of pi 1, but basically you take a pi 1 that
Mm,
gives you this smooth homotopy equivalence. You run through these theorems and reword that in terms of hyperbolic geometry, and you get all the things you could want. So in a lot of the work I've done, quasi-isometries and pseudo-isometries, and coarse geometry in general, gives kind of this toolkit for, if you have two things that, if you have nice enough objects that you need to upgrade to geometric structure, you can often find ways to lift those or to perturb those by adding extra structure, such that it upgrades to a quasi-isometry or a coarse equivalence. And that coarse equivalence will tell you that it didn't preserve all the structure. We it, so there's something that's missing, but it often allows you to preserve enough of it. And preserving enough of it is what allows us to carry over these geometric properties, because quasi-isometry carries over all of this stuff. Because quasi-isometry preserves like everything under the sun you could care about when it comes to
right.
geometry.
Okay.
Okay. Thank you so much, Brevin.
Yeah.
Thank you.
So,
It was. Mhm.
sorry, go ahead.
Yeah. No. What were you gonna say?
Oh, I was just going to ask what our plan was for the reading in this next time, because we should. So what's our plan for reading and for what's been covered?
So I can share my screen and I can share the survey and we can see where we are with the survey.
Okay.
Um, Screen. Da, 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 da. All right. I was just looking at, there were two surveys. One has more details.
Hmm.
So right now, I'm just gonna go over. We looked at theorem one. This is the Bedlewu. I don't know how to pronounce this still.
Yep.
And unless someone knows how to pronounce it, I will not know for the entire reading course. So we looked at a theorem one. We looked at the example, like what is asymptotic dimension for trees. We looked at large scale invariance of asymptotic dimension.
Mhm.
Brevin nicely introduced us to coarse equivalences, and we proved this proposition too. There is a corollary about the groups from this is coming from geometric group theory point of view.
Mhm.
So either we all can. I just want to take a quick survey if people are okay with it. How many of us are not familiar with finitely generated group and how to see group as a Cayley graph?
My impression is everyone who's currently in this call is fairly familiar with the basics of
Okay.
this stuff.
Okay. I think, how about you, Denise? Because I remember Denise has not taken geometry group theory class.
I know what it is. I haven't worked with it a lot. Like I could
Okay.
follow an argument probably, but
Okay. So do you think it is okay? All right. Okay. So Sagnik, I wanted to ask you for your help with this stuff. Do you mind presenting corollary 3 quickly next time, just from
Yeah,
the
sure. Sure, sure.
and And then maybe we all can look at examples. So last time, Brevin gave a nice suggestion about we can also do our own reading. So that this example, for instance, asymptotic dimension of R and Z is 1. We all can look at it on our own and try to reproduce the proof so that we don't go over it. And we can discuss if any one of us has a problem with the proof, we can discuss it then.
Yeah.
And this will be our common reading. And then Sagnik, maybe you can present corollary 3 and then example. So now here, Sagnik, I wanted to mention in the other survey I was checking. So they also mentioned something about one discrete metric space. Meaning of metric space is C discrete if distance between any 2 points is greater than or equal to C. For instance, I think it can also, yeah, anyway. So maybe, I don't know if, let me know, like, let us know next time if you would like to present proof for proposition 20 or not. It's
Okay.
fine. We don't have to cover everything. But from the geometric group theory point of view, like before union theorems, I was thinking we all take a look at these surveys, both surveys before the union theorems, so that next time we can finish until here. And I'll try to look at union theorems as well. If we have time, at least I would like to state proposition 24 or anything. And I remember, Ritvik, you also said you would like to present at some point. You're also free to look at the union theorem. So the goal would be to look at a finite stability. This corollary 26 finite union theorem is also called finite stability of asymptotic dimension. And that translates to finite, like the finite stability means that if your metric space is composed of components like A union B union C, then the dimension, asymptotic or Nagata dimension of your metric space is maximum dimension that you see in these components, like it's maximum of dimension of A, comma, dimension of B, comma, dimension of C. So it would be, this is an important aspect from dimension theory point of view. There are certain dimensions, like I just recently got to know last week that there is a dimension, Lipschitz dimension, in which this finite stability has not been proven yet. So this is an important, that's why people are a bit hesitant in implementing or trying out Lipschitz dimension. They don't try many of the proper this as a tool, because we this finite stability is something that matters a lot in many of the things. So for the next 2 weeks we have a tentative plan. Does this sound okay to everyone? Are there any suggestions?
I think it sounds reasonable. I think I would be okay with speeding up the course slightly.
Mm-hmm.
I don't know what other people's thoughts are on that, but I think we could potentially. I think that's a good program for the next couple weeks, but I think it's maybe something
Yeah.
to keep in mind that we're not on track to finish this paper, and I think we should be able to finish easily at least this one paper over the semester. So I think if we need to,
Mm-hmm.
I think we could probably get like 50% faster easily, and it would be like no issue whatsoever when it comes to reading stuff over the course of the week. Whatever it takes to make sure we get through all of this stuff in one semester.
Yeah, so how about I really like the way you presented today, Brevin. I think what we can do is going forward, one improvement that I would do in my own presentation is I will start writing very clearly or taking very clearly so that even if we don't go over all the proofs, we at least share our notes with each other. That could also speed up the course. How do other people feel about speeding up? Do you think that's reasonable?
I'm fine with it. Like again, so I'm not 100% certain if I will be able to keep up with everything because again, this semester has been going slightly wobbly. But I at least want to for the next few weeks we can try to see how a speed up goes. If we are not able to manage, I think I can at least still attend the meetings and get a basic idea of what's happening in the paper.
Mm-hmm.
Hmm.
So, Brevin, I think this survey in itself, I feel it's a very large or what's the right word? It's a lengthy survey sort of thing. So, do you think I feel that there is not, we don't have to touch on everything in the survey in order to see a finish line, but that's
Sure.
a very good question that you have mentioned. How about by next time or the week after the next, we all go through the survey just from the uh, just look at the headings of the survey and think about the areas that you care about the most in the survey. Then we make a list and then we see how to proceed so that we have a decent finish line which suits all of us,
Sounds fantastic. Yeah. Yeah.
right? Because going through everything will be a bit difficult,
Mhm.
according to me, because I have been trying to read this survey as well for a very long time. And given just 50 minutes, it is kind of hard to finish this.
Yeah.
Over 16 readings, it does not seem feasible. So, all right, take your time. Maybe in 3 weeks, we'll discuss what is our finish line and how to speed things up, or maybe in 2 weeks. But anyway, so all right, Sagnik and Ritwik, then let me know if you are able to look at this survey on your own. Ritwik, I'm happy to discuss if you want to just hang out in Google and discuss this about union theorem. I can go over the proof with you as well. So just let me know.
Yeah, so okay, I do have an exam this week. I will try to read up till union theorems. If I'm not able to present the coming week, I'm